All right, I want to just finish off with a few quick slides about power and look at the expressions that we can use for power either gained in a circuit or lost in a circuit. So in this picture, what we have is a conductor, and there's a potential difference from point 1 to point 2. And we're told that the potential at point 2 is lower than the potential at point 1. So as our positive charge carriers move from point 1 to point 2, the change in potential that they experience is going to be less than zero. Notice they're moving in the direction of the electric field, so they're moving to a decreasing potential. So if we think about the change in potential energy that these charges go through, and again, we're thinking of them as positive charge carriers, the potential energy change that they experience is also going to be less than zero. So they're going to be losing potential energy. And so we've talked about that in class, sort of looking as we travel through the circuit and understanding that there are times when the potential rises or potential drops, depending on whether you go through a battery or a resistor. But also then we can think about the fact that at these times, there's a change in potential energy associated with that change in potential. Now, finally, the next thing that we're going to look at is what about power? So power, if you remember, is the rate of energy transfer, or sometimes we think of it as the work per unit time, or we could think of it as the change in energy per unit time. And we're going to use that to try to figure out expressions for power in a circuit. So using the definition that power is energy over time, we can use the expression that we just were looking at. So the change in potential energy over time is the delta Q over delta V over delta time. But then remember that this expression, delta Q over delta T, is actually current. And when we talk about circuits, usually we don't use the delta V, we just talk about V. It still means the same thing to us. So this is one way that we can express power. And the idea is that as they presented it in the book, I think they sort of talked about, the power delivered by, say, the EMF or the battery, which of course has some potential and the currents running through it. So we can think about the fact that as the current travels through the battery, there's this power delivered to the circuit. And so in that case, there's going to be, an input of power. We could also use this to think about the current traveling through a resistor, which will experience a potential drop. And so in that case, there will be potential that power that's lost in the circuit. As we start to look at these different expressions, what I would say is you use whichever one seems to be convenient for you based on the information that you're given. But let's look at some other ways to write it. So we have just found that one way that we can write power is current times potential. And we're going to use Ohm's law to write it in some other ways. So for instance, what if I took Ohm's law and substituted for V, I times R? And so then we could say that the power could be written as I squared times R. And then what if we also took Ohm's law and rearranged it, and for the current we wrote it as V over R, and that would be, then I could write it as V squared over R. So it turns out that we have three different ways that we can express the power either lost or gained in a circuit. And like I said, it kind of depends on the how you want to apply it. As you see in this picture from our book, they prefer these two expressions when you're talking about a resistor. And then in those cases, it would be the power that's lost. And that's fine. You could use this expression for a resistor. I think that they focus on the last two because they have the resistance in the expression. But any one of these is going to be fine. And so, so I think that this is where there was some confusion, like, well, what is this power? Is it the power delivered or the power lost? And the idea is that all of these expressions can be used to answer either way. For instance, this could be taught. This usually is going to be talking about the power that the battery delivers, but you could use it for the power lost in a resistor. Now, these expressions we wouldn't use for a battery because a battery doesn't have resistance. And so when they have the resistance in them, we're really just going to exclusively use them for a resistor. The idea that as the current travels through the resistor, there is a resistance to the flow of current. And because of that, there's energy lost, power is dissipated. Usually that power is going to be dissipated in the form of heat. So I wanted to look at this example again and to sort of look at it from the viewpoint of power. Just to remind you, I found that the current in this circuit was 0.1 amps. And so we could look at, first of all, the power delivered by the battery, and that would be 0.1 times 9, and so that's going to be 0.9 watts. So that's the power delivered by the battery. And now, as we go through the circuit, we might want to use I squared R for the power that's being dissipated by the resistors. If we do that, we find that through this circuit, we're going to lose 0.2 watts through that resistor. This is going to be the same for all the 20 ohm resistors because it's the same current and the same resistance. And then for the 10 ohm resistor, we would get 0.1 watts. And if you look at that and look at how the values compare, you notice that we have gained 0.9 watts of power was delivered as the current traveled through the battery, but then we lost 0.2 watts through the first resistor, another 0.2 watts through the second, and the third, and the fourth, and finally through the fifth we lost 0.1. And notice then, if we add these all together, we get to 0, which is similar to the idea that we talked about with potential and with potential energy, is as we go through the circuit, there'll be gains and losses, but in the end, when we come back to where we begin, we'll be back at 0. So here's a question for you to think about, and I'm going to leave this to you to think about. And they want to know, in these two circuits with identical bulbs, if you have two light bulbs in the circuit, and then you change and take one out, how will the brightness in the bulbs compare? And a hint is that the brightness is going to be reflected by the power that's dissipated in the bulb. So what you want to be trying to think about is how will the brightness or how will the power delivered by the battery and dissipated by the bulbs compare in these two different circuits to figure out which one is brighter. All right, so that's it for power, and next time we will be moving on to looking at combinations of resistors in circuits.